So now, if you're going to analyze back the same question here, okay, let's see here. How are you going to analyze this? Let's see.我先给大家一点应用背景。所以刚才我们已经讲过这个叫，所以 you now going to analyze the question. If you now have the length of 1/3 the length, this is another 1/3, and finally this is another 1/3. Okay. If you are doing the lumping of the force, how do you write? Okay. You write this is 1, 2, 3, 4. There are 4 nodes here. Then you're going to have QL over 3 divided by 2. So this is 1/3 of the length. This is now QL over 6 for these lower parts. And then the middle part, you have QL over 6. This is QL over 6. So apparently, when you add them up, this is QL over 3. For the top part, what do you have? For the top part, top node is QL over 6. Bottom node is QL over 6. And you add up, this is QL over 3. So you can see that if you are using the consistent division of the total force, you are distributing the total force onto the nodes. If you follow the previous rule we did, you are going to have the force distribution of QL over 6, QL over 3, and then eventually QL over 6。所以看到现在给你看到的是一个力的分布 ，OK， 那这个分布图大概是长的这副样子。那当然，你如果说有就是等重分布，那后面你的写法就不一样。So this is how we do something. Okay. But very important thing here is how do you handle the distributed force? If the force is distributed, then you're going to have distributed displacement. Okay? Meaning the strain is changing over the space. But in this state, if you are saying this is a constant change of the displacement, how much is the strain? Okay, how much is the strain if you are assuming constant one? So if this is U1, it eventually comes to become U2. Let's write the expression here. The displacement along the length at any point is ux. It can be written as 1 minus x over L u1 and then plus x over L u2. Okay? So meaning the displacement can change. Okay, if you now do a very quick strain definition, what is the strain definition here? What is a longitudinal strain? This is the displacement. How do you get the longitudinal strain? 我们问一下同学，应变怎么定义？问一下，右手边。 上面会以 U 啊，下面会以 U 圈上来。一边是多少？一边是多少？什么东西 ？U2 减 U1，然后。所以 yes, the difference. If this is the difference, this is just an extension. You still have to divide by the percent. Okay? So this is what you define your engineering longitudinal string. The bottom displacement divided the top displacement is the total extension. So if it happen that bottom and top move the same, then you have zero strength, you have rigid translation. And then now, engineering wise, how do you define strength? Engineering wise, if you are going to define strength, you are not taking the total piece. You are taking a small piece. If this is location X, you might have displacement X. And then after the small piece, then you might have displacement Ux plus dUx dx. 各位看到没有？这个是一个一小片，可以讲是切片，一个杆的切片。这个点是 x， 下面这个点是 x 加 x。那位移呢？位移就是从 ux 变成 ux 加 dx。So if you want to find out the strength, okay, you take the difference. The difference here is the difference of the top and the bottom. Divided by the top displacement, bottom displacement minus the top. Okay. Likewise, you then have infinitesimal strength. I think it is the local strength. So in the end, your strength definition is du dx times dx divided by dx. So then you have dUx. Okay. So based on this, what are you going to have? If you now do this derivative, if you do the derivative, if you now take that out, you're now going to have minus 1 over L U1 plus 1 over L U2. It is then U2 minus U1 divided by L. Okay. This is important. Why? If finite elements is going to be valid, it must follow your engineering rule. 所以有限元素有一个验证的很重要的方法，不管你的公式多么复杂，你化简到最后，你一定要跟工程上的定理一样。比如说，刚才常数的应变，刚才我们说的是这个杆的末端跟杆的上方的位移差除以全长，就是应变。那我们刚才用的这个内插法去做中间位置的位移的一个预估。那我直接拿随便中间位移去做微分，那它得到的应变还是一样。Okay, with this, we're going to show you, based on these interpolations, we're going to obtain the stiffness matrix as well.
对大部分同学而言，其实是位移场的概念。那我们后面得到的那个矩阵应该都是一样的。那我们先介绍一下。Okay, so just now we will tell you if there is a block, we got not 1, not 2, not 1 for displacement U2, not 2 for displacement U1, U2. Then the distribution is linear. If this is linear, how do you get the shape function? Okay, I can use linear interpolation by writing Ux equal to A0 plus A1x. So this is a linear function. I have to write the boundary. What is the boundary for this interpolation? At x equal to 0, u is u1, meaning when x is 0, a0 is u1. Okay? So you already find your a0. Second, when x equal to l, ux is equal to u2. Then you have your u2 is equal to a0 plus a1. L. What is your A0? According to the previous calculation, A0 is equal to U1. Now you can find what is your A1. Your A1 is the difference of not 2 displacement and not 1 displacement divided by the length. This is almost like your strain definition. And now, by substituting A0 and A1 back into the linear interpolation function, I can find Ux is equal to U1 plus U2 minus U1 divided by L times x. 所以这个公式怎么理解？这个公式很简单啊，它基本上是你这一点的位置的位移，就是上一个点的固定位移，再加上应变乘上位置。OK， 那我们现在的目的不是去把这个函数写成位置的函数，我们目的是把它写成形状函数。比如说 U1 乘上形状函数 ，U1 的影响有多少？U2 它的形状函数就是 F2。So the purpose now is to generalize the interpolation. U1 can be anything, but my N1 is going to tell you the inference. At x equal to 0, U1 is 1. At x equal to L, U1 contribution is 0. Likewise, you can do the same. At x equal to 0, N2 is 0, so that U2 has 0 contribution. At x equal to L, N2 is 1, so it's going to be U2 100% contribution. 所以我们把这个位移场的分布假定成末端位移都知道，末端位移即便是不知道，也可以通过这个有限元素计。So we are assuming that the normal displacement can be solved. They are treated as boundary. So any displacement in between are just the interpolation between the. So in a way, if I have my displacement written as shape function U1 and shape function U2, I can find my strain by differentiating the shape function. 1 minus x after the differentiation is minus 1 over L. And then the N2 after differentiation is 1 over L. In this way, we can write your strain as this strain is du dx is equal to derivative of shape function 1 times U1 plus derivative of shape function 2 times U2. As a result, I can write my strain as B matrix times U. This B matrix is a strain displacement matrix. Okay? And then next, if you already do so, I have obtained the strain. Next, I can write my strain energy as stress times strain, integration over the space divided by 2. And stress is equal to Young modulus times strain. As a result, you you're going to have the strain square. Strain was previously written as a vector form. Okay, if you want to write into scalar form, it's also okay. They are the square of these B matrix and displacement vector. Okay, if you expand them out, you have the shape function gradient square times displacement square plus product of two shape functions gradient times displacement. Then final term is actually determined by the gradient of the second shape function and displacement 2. Okay? If you now do partial differentiation, okay, you can reduce the expression into simple form like this. Okay, for partial differentiation with displacement 1, you obtain force 1. For partial differentiation with displacement 2, you obtain force 2. If you write the two equations together, you're going to obtain the expression something like this. Again, if you do the substitution in, okay, then I'm going to obtain the same stiffness matrix. 刚才那个做法，等你去做完过后去解，它得到的还是一样，跟你的这个方程式是一样的。好 with this, then we are done. No, is it? We are supposed to have more time here. 好，我们再继续。So let's summarize what we did. Previously, we assumed finite element is just a rod subjected to tip forces. You only need to solve for the tip equation. Okay, now you assume it to be a continuous rod. Okay, it can be subjected to body forces. Okay? So we have tell you the force of some of the displacement. Okay, so how do you obtain this du dx? We are doing the linear calculations. You can find this chain. Okay, but we haven't do the force sum on the rod. If you do the force sum on the rod, okay, you can also do the same. Some point. So we are transiting somewhere from rock as a discrete element into a continuum. What is it the difference? Previously, so you only care about n displacement, n forces. Okay. But now, if it's continuous, every force will be subjected to some sort of force. Okay? Yeah. And because you might have a small rock, you might have a big rock, the area can be different. Okay? So to describe the difference, I think force is not a good way. So that's why we define stress. Stress is F1 divided by cross-sectional area. Okay? We now consider uniform rock. It will happen that you have non-uniform cross-sectional area. So if that's the case, so this is going to be different. Okay? The cross-sectional area could be a function of displacement as well. Okay? So next, if you're going to describe this kind of thing, one way to write this is, this is the force at point X. This one is force at different location. Okay? So if you write this force, I think Taylor series tell you can do the interpolation. You can write this as force X plus X, X. Okay? So to get it clear, because it's depending on the area, you can write this as divided by area. Then you have the stress X. Then you can write this as stress X plus B sigma X X. So if that's the case, how much is the force balance? Okay, according to your what I'm going to write. According to your basic understanding, okay, Newton's law tells you force F is equal to 0. Okay? You do the same. You're going to have stress X forward, both are equal. Depending how you write them. If you want to write the fundamental calculus, okay? You have to write if you after you do the correction of the sign, okay? This one I'm going to consider the sign. After the sign correction, you're going to have, okay, let me write the force on the left. Force on the left plus force on the right is equal to 0. Okay? Then, after divided by the area, then you got the stress on the left plus stress on the right plus chain of the stress X equals 0. Okay, in this way, you eventually come to the equilibrium equation. The chain of the stress is equal to 0. Okay. So we're going to write this. Okay. This is what we call your force balance equation. Also called the equilibrium. 所以你要注意的是，老师在这边画，因为大部分课本都是写公式，那公式的由来是什么？其实都是这些力。对，大部分时间大家花很多时间在画。So in this way, we're going to obtain the expression here. So this is just the starting, and okay, and this one. What is it important here? We haven't used this equilibrium equation yet, but I'm just telling you just now if you're using the strain energy expression, upon substitution of the u dx, you're going to eventually obtain the partial differentiation of the strain energy with respect to u1 is equal to this expression. Okay? This is not going to be equal to the stiffness equation. We're going to show you how you use it next. Like I just said. Okay? 那后面我们有了这个分布的位移 ，OK， 这个重点就来了。位移场，你可以把它想象成是一个函数。那位移场有个特征，它的边界是被固定的，所以你会知道它边界的领域或非领域。OK， 那你要把这个位移场求出来。 你是可以用这个近似差法。So if you're going to describe the displacement field within the boundary, let's say from x equal to a or x equal to b, then you can do interpolations. What kind of function that can be interpolated? Very simple. You can describe linear segment, or you can describe a nonlinear function. A simple nonlinear function that describes this is how do you force the boundary to be 0 on x equal to a. Then that function must have a term x minus a. How do you force the function to have x equal to be 0 and x equal to b? Then you must have the function x minus b. So the total function can be product of x minus a and x minus b. Okay, so how do you do the forcing of this interpolation? You can't make sure the differentiation equation is 0, but you can multiply it with some weightage, and that weightage is your shape function. You want to force it to be 0. So that's why we call it weighted Gaussian method. Okay, so I will go through with you how this kind of interpolation function can be useful. Okay, take for example, I'll take the example, second order derivative of y minus 10x squared is 5. Okay, if you learn your calculus, you can do your integration without a problem. Okay, let's see the analytical solution. If second order derivative of y is equal to 10x squared plus 1, one-time integral will lead you to cube plus x plus c. And second integral will lead you to x to the power 4 plus x squared plus x plus constant. And how do you find the unknown coefficient c and d? You reinforce the boundary. As x equal to 0, y is 0. As x equal to L, and as x equal to 1, 1 is also 0. So upon doing the substitution here, then you can find what is the C, what is the D. So eventually, you got the analytical solution for y, which is 5 over 6 times x to the power 4 plus 5 over 2 times x squared minus 10 over 3x. So this is your analytical solution. Okay? So now, what are we going to show you? We're going to show you that we can assume a function that fulfills the boundary and force it to approximate the analytical solution. So how do you do the forcing? Very simple. When x is 0, y is 0. When x is 1, y is 0. What kind of function can meet these boundary conditions? Very simple. X minus 0 times x minus 1 is going to be the function that fulfills the boundary. The only thing that is unknown is what is the coefficient. Okay, so it is clear x is 0. Y is 0 when x is 0, and then y is 0 when x is equal to 1. So let's write this shape function. This shape function multiplied my previous boundary condition, multiplied my previous differentiation equation. Okay, with the coefficient C1. Okay, let me write that. 这个写法有时候是因为它是做那个写的步骤，但是可能听不清楚。We're writing we're trying to solve this equation. Okay. Can you find the answer? What is it? So now you're going to do the approximated answer. What is the approximated answer? Because we know this function is 0 when x equal to 0. And this function is 0 when x equal to 1. So this approximate function I can write that as x c times x minus 0 times x minus 1. So then you're going to obtain cx square minus x. Okay, if you do one-time differentiations, you got c 2x minus 1. If you do a two-time differentiation, you got c times 2. Okay, so this is the expression. But now what do we want to force? Okay? We want to force these to be fulfilling the constraints. Okay? We want to find what is my C. Okay, I don't know my C value here. Okay, I want to force it. To force it, I need to know the difference. Okay? This is the equation I want to solve. Okay? The residue of term must be 0. You know what I'm saying? This is the expression of residue. But this is exact. Okay, this is exact 0. It cannot be that precise. If it's not cannot be that precise, you define your R to be shape function times R, and then you go to do the integration over the space. You force this to 0. Okay? If that's the case, you do this substitution here rather than using your Z1. Okay, you're going to write C x minus 1 times what is? This is my 2C. And what is your y star? Your y star is minus 10 x squared x minus 1 squared, yeah, and minus 5. And then you integrate these with respect to x, and you force it to be 0 to find out what is your c. Okay? And if you are not sure what this is, then you do the expansion. You're going to have c x squared minus x, okay, times the expression here. The expression is minus 10 x cubed plus 10 x squared plus 2c minus 5 dx. So this is a complex expression, not to worry. You will look at it.同学看到没有？你这个目的很简单，只是说，反正边界都条件都满足了，中间，那你随便取。那取也有一个规则，就是它的这个实际值跟近似值的差要趋近于零。那趋近于零，你有很多做法，可以做这个加权法。那我们通过这个方法。任何微分方程，你都可以用一个近似函数去表示。OK， 这个近似函数是挺复杂。那我们现在也可以拿简单的近似函数。We can do the simple one. Okay. So now we come to the point of this integral method. Okay. So how do you get these expressions? Okay. So I'm not going to go through the detail with you, but I just tell you the fact. Previously, when you're writing your governing equations, when you're writing a book score, when you're writing strain and displacement relationship, you can combine them to make the second order derivative of displacement is equal to 0. And because the displacement is interpolation function of the boundary, okay, then you're going to be able to write this Gallatin residue method. Gallatin residue method, it is your shape function times your governing equation. And then it's equal to, you can do the integration by parts to eventually find the same stiffness metric expressions as you did just now. Okay. 对，所以这一题这个部分的目的是什么？这个部分的目的是告诉你，你的感可以是一个离散的一个，你用五个定律去叙述，你可以得到 ，you can find out the truss equation using the assumption of discrete truss. Okay, but at the same time, if you treat it as a continuous rod, you can solve it using the energy method. Okay, and then next, if if you now consider finite, very small element of the drop, if the drop is continuous, you can still using the residue method. So what do we do now? We are doing the evolution, we are revisit the evolution of finite element. Finite element can be structural element, it can be generalized element, still structured, but you are using energy method to solve it. But now we turn it into mathematical problem. This mathematical problem is what you call boundary value problem. So every governing equation is a second order differentiation. Okay? If you now assume the right interpolation function, you can always turn any governing equations into these kind of discretizations. Okay? 那我们可以拿一个简单来解题来看一下。所以我们这个过渡是有原因的，就是说，你结构分析其实你的弹簧度好了，那你不用搞得这么复杂。那这么复杂的原因是什么？你可能要考虑应变。Okay. So take for example, this is a question about thermoelastic expansion. How do you predict a finite element from raw subjected to thermal expansion? Okay. So you might have a complex one. Okay, but later I'm going to go through with you the simple one. Okay. So what makes a thermal expansion? A rod, you can hold it by force. It has elongation. A rod, if you heat it up, it can expand more. Expand more by how much? L alpha delta T. So meaning, this is the mechanical cooling, but by heating, the extension is going to increase without increasing the force. Okay. So now the strength. How do you define mechanical strength? Mechanical strength is total elongation minus the thermal-induced elongation. So the thermal strength is thermal-induced elongation divided by starting length. And that strength divided by temperature rise is what we call thermal expansion. Okay. Then next, how do you achieve the elongation by heating? If you block the rod, they will induce a block force. KL alpha delta T. So if you think the other way, can I make thermal expansions equivalent to a pulling force? Yes, you can think so. The pulling force is opposite of the block force. Block force is a compression. And equivalent pulling force is the spring constant times length times the thermal strength. Okay. So this is how the external loading can be. Okay. And then next. Okay, a rod subjected to thermal expansion. Okay. You can see that if you block the left hand side, the right hand side is moving rightward when it thermally expands. So this is equivalent to what? Thermal strength times the total length is thermal expansion times the spring constant. You're going to have equivalent pulling force that causes thermal expansion. 所以你在刚才做分析的时候，就是说，即便你没有外力，但是你加热的效果，右手边是向右的拉力， 那左手边呢 ，if you now rock the right hand side, the left hand side is free to extend. You feel free to extend leftward. Okay. So this is equivalent to what? That is equivalent to left pulling force. So to describe the force acting on these elements to produce thermal expansions, you must have the right pulling force rightward. You must have the left pulling force leftward. So the left thermal pulling force is negative. Okay? So if you do nothing, okay, no heating, this is the external force is equal to the elastic force for the thrust energy. But because of the thermal expansions, you see that even if you have zero force externally, heating will cause the right hand side to elongate. Elongate by how much? The elongation must be equal to the one caused by right thermally induced pulling force. Okay. Left one is negative one is a leftward thermally induced pulling force. Okay. 所以我基本上是先教你们物理，因为毕竟公式已经非常乱了。OK， 当然很严谨的话，你一步一步做是可以得到一样。但是我们直接先讲结论，你有了一个物理的了解。So we tell you the conclusion first. This is the one that you're going to use, and that you're going to check using this formula. For any rod subjected to thermal expansion, okay, you are always writing it. Okay, so let's see. If you now have the rod being heated up, it's going to expand toward the top, it's going to expand toward the left. So this is not equivalent when you have the thermal pulling force. It is the spring constant times thermally induced elongation. And this one is the spring constant times thermally induced elongation. But clearly you can see the direction is opposite each other. Okay? And now, if you turn this to be 45 degrees, the thermal force is still the same, but inclined to be parallel along the axis of the rod. Okay? 所以在这个部分，同学能不能解题，不在于你的数学。一开始是你要知道它这个热膨胀造成的等效热张力 ，OK， 它的方向是 ，OK， so we will tell you the workout yet, but we tell you the conclusion, OK. And then next, how do you do the right working out? Okay, so this is going to be solved using the weighted residue method, but for the ease of understanding later, I'm going to show you by the energy method. Okay, yeah, this is by energy method. Okay, let's see here. What is the strain energy? The strain energy must be a mechanical energy. It should exclude the thermal strain. Okay, see here. Strain energy must be pure mechanical energy. The energy that is caused by external pulling force. Any heating won't contribute to the strain energy. So I have the strain, total strain minus thermally induced strain. Likewise, what is your stress? Stress is mechanical stress. Okay? It must be Young modulus times net mechanical strain. which is total strain minus the induced strain. Okay, if you now do the expansion of the strain energy, okay, you have the strain, total strain square minus 2 times the absolute strain and thermal strain plus the thermally induced strain square. If you're now doing the integration of this expression, okay, you can have expansion of this. Okay， 我们现在的应变，跟刚才一样，你任意场的应变基本上是两端的位移，各乘上它的形状函数 ，OK， 然后再对你的空间场做偏微分。OK，so let's see. And then eventually you are writing this expression. Okay, I'm working with you on how to write this one time. Okay. Case you have a rock. Okay, previously you might say K, U1, U2. This is a discrete rock. But to describe the same thing, you can say this is the one E, A over L. You have K. Okay. You have boundary U1, U2. Any point here will move by ux. Okay. This is the first step we describe the displacement. Okay. Toward the boundary here, at x equal to 0, ux is u1. At x equal to L, ux is u2. Okay? You know at any point when you have displacement ux. How do you describe the ux? To describe the ux, we invented the shape function. Okay, what is the shape function here? The shape function is 1. Shape function n1 is 1 at x equal to 0. shared function n1 is 0 when x equal to L. Okay? So why do you do so? Because if you do so, your ux, which is n1 times x times u1, will fulfill the boundary on the left hand side. And then next, you now have shared function n2, okay, which is 1 at x equal to L. This is n2x u2. Okay? After all, these are all interpolation functions. If you go and check the u1x, this is 1 minus x over L times u1 plus x over L times u2. Okay. So for the first time, you are able to interpolate the displacement. This is the displacement interpolation. Okay. Yeah. Okay, then next, how do you find the forces? Okay, we haven't talked about the thermal one, but I go through with you the elastic one. Okay, and then we also tell you the local strength. If this is location x, it has the displacement ux, and this is dx, it has displacement ux plus dx. So you can find the strength is equal to ux plus dx minus ux divided by divided by the x plus dx minus x. So then you have the du dx. So this is what we define. And then recalling your Hooke's law. How much the strength? You might previously have force versus displacement. And if you now divide the length, divide the area, then you're going to have the stress and the strain. So now you're going to have Young modulus and the strain is equal to Young modulus du dx. And how much is the strain energy? The strain energy is the stress and the strain times the volume. Okay, how much is volume? The volume is cross-sectional area times dx. Okay. 所以大家看到，所以这个是我们从一个结构的角度来做。我们先把这个静结构做完，然后再考虑热。First analyze the pure structure. Okay, so we already obtained the strain energy expression. Okay, what is the displacement? Displacement at any point is n1 u1 plus n2 u2, and then the strain is du dx. Remember, this one is 1 minus x over L. This one is x over L. I can do differentiation of them with respect to x. Okay? So this is the n1 dx u1 plus the n2 dx u2. Do I need to differentiate u1 u2? No. U1, U2 are variable, independent variable. They are not depending on the location. Okay, they are to be solved. They don't change with location. Okay, that is a fixed solution. Okay, so if that's the case, what's your stress? Your stress is this expression. And then what is your this strength energy expression? Strength energy expression. So let's do the expression. It is the expression that it is EA, and then you take the strength square. Okay, the strength square, if you take the strength square, you have N1 gradient U1 square plus 2 times gradient 1 and gradient 2 of the shape function times U1, U2. Plus the gradient of the second shape function times U2 squared, and this is dx. Okay? Yeah. This might appear rather complex, but don't forget, if you remember your Castigliano theorem. What is your Castigliano theorem? Not one force equal to the partial differentiation of the strength energy with respect to displacement 1. Okay, this time round, it is partial differentiation with displacement. So now you have the EA integral. Okay, this one becomes 2 shape function square, shape function gradient square, times U1. And then for the second term, it is 2 times dn, the shape function gradient 1 times shape function gradient 2, and then du. And then this one is integration. Okay. And how about the cos 2? Cos 2 is the partial differentiation of the gradient, strength function with respect to U2. And this is the EA. And then now, 2 shape function gradient 1 and shape function gradient 2 times U1 plus, what's next? You have 2 times shape function gradient 2 square and then U2 x. Okay. So with this, now we can write the force into the matrix form. Okay? So you are writing force 1, force 2. And what is the second term? The second term is EA, a stiffness, okay, times U1, U2. Okay? Let's identify the gradient and variable U1, U2. You're going to write this. Okay? At the same time, this whole thing should be expressed as the integral along the length. Okay? This is the integral along the length. So let's first write the first equation. This is, okay, previously I think it should be divided by half. Okay, I forget to do this. After you take all the half, these two terms are all gone. So you now have shape function gradient 1 square times u1, and then shape function gradient 1 and shape function gradient 2. Okay? And likewise, you now do this second row of equations. Okay? Now do that. Then you have shape function gradient 1 and shape function gradient 2. And then this one, n2 x squared. Okay? This expression. So now let's do the substitution of the value. n1 is 1 minus x over n. The n1, the x is minus 1 over n. n2 is x over n. The n2, the x is 1 over n. Okay, you do the substitution in. Okay, what do you have? This one is minus 1 over L squared. This one is minus 1 over L and 1 over L. This one is minus 1 over L and 1 over L. This one is positive 1 over L squared. Because they are all constant. If you really do the integration of x from 0 to x, what do you have in the term here? You're going to have x over L squared minus x over L squared minus x over L squared, x over L squared. If you do this integration, then you're going to start from x equal to 0 to x equal to L. So in the end, what this expression, this is going to be 1 over L minus 1 over L minus 1 over L minus 1 over L. If you do the substitution back, what do you have for this? If you take out the L, this whole expression reduces to E A over L, 1 minus 1 minus 1, 1. So this is now your trust element again. If you are using your energy method. Okay? Now here comes what is stress. Okay? So a quick one. How to handle the stress? Not difficult. Why? This is the absolute strength. If you want to find mechanical strength, this must be the total strength minus the thermal strength. Okay? If you are going to find the mechanical strength, this expression must be mechanical. So this is minus the thermal strength. Okay? Likewise, this is all mechanical strength energy. It must be mechanical stress and mechanical strength. Okay? If that's the case, your expression here must be written to be something minus the thermal strength. Okay? So let me do the expansion of that so that you can have a quick answer. Okay, if you now starting from this term, UE is half mechanical strength and mechanical strength, and then area to the length integration. So this expression, I can write it Young modulus times total mechanical strength is then the total strength minus the thermal strength squared. Okay, if you now do the expansions, you're going to have EA over L, then you're going to have this gradient square minus 2 thermal strength gradient plus the thermal strength squared dx. Okay? This is my mechanical strength. If I'm going to find this force, my force one is the strain energy, partial differentiation of strain energy with respect to U1. Okay? So how are you going to solve this? Okay? Immediately you can see, if I'm going to take gradient, okay, I must have EA, okay, this is divided by 2, and then this is 2 du dx, and then what else? And then you are going to do the partial differentiation of del U1. Okay? Likewise, this one is minus 2. Okay? This is the del du dx del U1. And final term, because this is a constant, so this is 0. Okay? So how do you do this? Okay? You see, in the expression here, the right hand side, the first term are exactly equal to my expression here. I only need to care about what is del U, del X, del U. Okay? Remember your U? Your U is N1 U1 plus N2 U2. If you write the expression du dx, it is dN1 dx U1 plus dN2 dx U2. If you now do the partial differentiation with respect to U, okay, del du dx partial differentiation with U1, you are only leaving out this term. Del N1 dN1 dx times del U1 and other term is 0. Okay? And if you now do partial differentiation with du dx with respect to del U2, then you have dN2 dx del U2 del U2 都反映不一样。OK， 好，所以你的方程式后面要怎么写？说实在的，来，我们来抄到这里来。大概一个总结。好，你看到没有？你要记的现在是这一项。So what is the thermal force? The thermal force is equal to what's that? After you divide by 2, then you have your strain energy times your strength, the thermal strength, times this partial differentiation with respect to the U1. And then you integrate it with X. 我们来积分一下这个热 而且常数这样带出来。然后这个刚才跟你们解的这个是第一项。What's the first one? It is the del n1 del x the del u1 del u1. So this term is equal to 1 x. So what is this? n1 is equal to 1 minus x over l. You have the dn1 dx equal to minus l over l. So what do we have here? So now we have the EA strength, thermal strength, and minus 1 over L, and then dx. So this expression is becoming minus x over L, from x coming from 0 to L, so you have 1, minus 1, so you have minus EA thermal strength. Okay? How about the second thermal strength? Second thermal strength was on the right hand side. You have the EA thermal strength times the gradient with respect to U2. Okay? What do you have? You have the expression of EA epsilon E times what? Strength gradient of dn2 dx and then dx. So what is expression? This is x over L. After the derivative is becoming 1 over L. So now your integration is EA thermal strength times x over L, when x integrating from 0 to L. So in the end, you have your EA epsilon E. Okay, if you now draw on the rod, what do you have? Okay, if you draw on the rod, if x is 0 here and x is L here, now your shape function N2 is this direction. Shape function N1 is in this direction. And then your spring force, the thermal induced force. Thermal force here is negative, despite positive excursion. Thermal force on the second knot is positive. Okay? They are equal, but opposite in sign. Okay? With this, we are done with the proving of the thermoelastic problem. Okay? 所以看到没有，我们搞了一大堆数学，只是证明了简单的热的张力。OK， 张力已经是相反。好，今天课就到这里。